Welcome to my channel. In this episode, we will solve the following thermodynamic problem. 1 mole of an ideal gas is taken from an initial state of temperature T1 and molar volume V1 to a final state defined by T2 and V2. Show that the corresponding change in entropy is given by delta S equals to Cv ln T2 by T1 plus R ln V2 by V1. And the second part is an ideal gas undergoes an adiabatic expansion from state some P1 V1 to the state P2 V2. It is then compressed isobarically to P2 V1. Finally, pressure is restored to P1, that means increased to P1, and at constant volume V1. Show that the efficiency of this cyclic process is eta is following, where gamma is equals to Cp by Cv. First part, we know TdS equals to du plus PdV, where T is the absolute temperature, ds is the change in entropy, du is the internal energy, P is the pressure, V is the volume. And du is Cv dt plus Pdv. For an ideal gas, Pv equals to nRT, n is 1 here, say. This is our equation of state. From here, from equation 1, ds is equals to Cv dt by T R by V, because from here P is basically RT by V and T cancels out. And if we integrate from some 1 to 2, S1 to S2 or T1 to T2 and V1 to V2, after integration we get delta S equals to Cv log T2 by T1 plus R log V2 by V1. In the second part, first adiabatic expansion from P1 V1 to P2 V2. This is the adiabatic expansion from 1 to 2, and then isobarically compressed from 2 to 3, and then pressure is restored to P1 at a fixed volume, at a constant volume, and this is the following PV diagram. Therefore, the work done by the system in the cycle above, W equals to the closed integral PdV from 1 to 2, 2 to 3 and 3 to 1, 1 to 2, 2 to 3 and 3 to 1. Therefore, and we know the adiabatic work done is some P2 V2 minus P1 V1 divided by 1 minus gamma. It is already known to us from the standard text we exercise. And here P2 is constant, P2 there is only change in volume, V1 minus V2, and here volume is, there is no change in volume, therefore this is 0. And if we just do some algebraic manipulation, we will get something like this. You can do at your own. Now, in order to calculate the efficiency, we need how much heat is absorbed. Heat absorbed is basically CVdT, and from the ideal gas equation PV equals to RT, V is basically constant, therefore VdP equals to RT dt and dt equals to VdP by R. In 3 to 1 there is only heat absorption, because volume is fixed, its pressure is increased by changing the by changing this. Therefore, if we put dt here, that is dp by R, and if we integrate from some value, say P2 to P1, and we will get this. And we know from Mayer's relation, Cp minus Cv is R, and from here Cv by R is 1 by gamma minus 1, and we put that thing. So amount of heat absorbed, Q equals to V1 by 1 minus gamma P2 minus P1. I just reversed it. Here gamma minus 1, here I put 1 minus gamma. And now from the equation 3, this is the work done divided by this heat absorbed, that is the efficiency. 1 minus gamma here, 1 minus gamma, that cancels out. After simple manipulations, is of this is a basically algebraic manipulation, you will get the efficiency is something like this, as described in the question here. Thank you for watching. If you have any questions or query, you can say in the comment section. You may subscribe, like and share.